All right, in this document, we're going to go through and we're going to be looking at position, velocity, and acceleration. But in these prompts, very often you can be given on free response questions, not necessarily functions, but just information presented to you in tables and graphs. So it's not always as simple as just finding the derivative of a function and plugging in numbers. And so I just wanted to kind of expose you to that a little bit and do a little bit of practice with it. So in this problem, we have a table where train A runs back and forth on an east-west section of railroad track, so it's a straight line. Train A's velocity, measured in meters per minute, is given by this function, where time t is measured in minutes. And then we're given selected values for that train's velocity given above. So at time 0, train A's velocity is 0. At time 2, train A's velocity is 100, and so on and so forth. And so the first part that it wants us to do with this problem is it wants us to find the average acceleration of train A over the interval 2 to 8. So remember, average acceleration, we're not finding instantaneous. So average acceleration, we're going to kind of go into the format for slope. So y2 minus y1 equals x2 minus x1, or in more formal language here, if we're finding average acceleration, that's your change in velocity over time. So we're going to find v sub a of 8 seconds, because we want to do it from 2 to 8, minus v sub a of 2 seconds, all over 8 minus 2. This would be the change in velocity over time, so this would be the average acceleration. And so we use our table to do that. So v sub a of 8 would be negative 120. V sub a of 2 would be 100, and then 8 minus 2 is 6, so we're left with negative 220 over 6, or in a more reduced fraction, negative 110 over 3. Our units on that would be meters per minute squared, because I'm doing velocity, so meters per minute, divided by time, your dependent variable over your independent variable. And there you go. So that's finding average acceleration, and this isn't necessarily using a function, but it's using a table of values. All right, let's talk about this next problem. A squirrel starts at a building A at time t equals 0 and travels along a straight horizontal wire connected to building B. For 0 to 18, the squirrel's velocity is modeled above. So this is a velocity function. So v of t is on this side. And they want to know at what times in the interval 0 to 18, if any, does the squirrel change direction. Now, we've talked a little bit about what changing direction means. Changing direction, or when your squirrel changes direction, we know something very specific about it. We talked about it a lot with when you're shooting a rocket up into the air, right? So we shoot our rocket up into the air, it changes direction, it comes back down. We talked about what very specific thing do we know about that rock at that time. Well, we know that technically it's at rest at that time period. Same thing if you're driving a car, you can't be driving forward and then switch to driving backwards without stopping first. And so we know that if your squirrel is changing direction, that would mean that your velocity of your squirrel would have to equal 0, and then it would actually have to change direction. So your velocity would either have to go from positive to negative or negative to positive. Because if your squirrel, for example, was traveling, so traveling, and then it stopped and just rested for a second and then kept going, then your velocity would be positive the whole way around. But in this scenario, they want to know specifically when it changes direction. So we have to find where velocity equals 0 and either goes from positive to negative or negative to positive. Since this graph is a graph of velocity, this stuff up here, or at least this section of the graph up here, would be considered the positive section of your graph, and this section down here is negative. And so my squirrel's velocity started off at 0 and then was positive, and so your squirrel's traveling forward, traveling forward, traveling forward, traveling forward, traveling forward. Here it hits 0 again, and then your squirrel its velocity goes negative. So I would say at t equals 9 seconds, my squirrel changes directions, and then my squirrel's velocity is negative, 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 hits 0 here, and then becomes positive, so then t equals 15. You have to give a reason for your answer, and so we would say t equals 9 and 15 because the squirrel's velocity equals 0, and your velocity changed signs. at those times. All right, let's look at this problem. So it says the velocity of a particle moving along the x-axis is modeled by a differentiable function v, where the position x is measured in meters, time is measured in seconds, so your velocity is measured in meters per second. That makes sense. Selected values of v of t are given in the table above, and the particle starts at position x equals 0 or x equals 7 meters at time t equals 0 seconds. They want us to estimate the acceleration of the particle at t equals 36 seconds. Now, I can see right off the bat that we're going to run into a bit of an issue because I don't actually have the time 36 in here. And luckily for us, though, the best estimation of an instantaneous rate of change, and you can write this down if you want. So best estimation for an instantaneous rate of change is the average rate of change closest to that time period. So basically what I'm saying is if you want to estimate how fast the particle was moving, or excuse me, the velocity of the particle at 36 seconds, but I don't actually know the velocity at 36 and I don't have a function to work with, what I can do is I can find the average rate of change from 32 to 40 seconds, and that's going to be my best estimate for the instantaneous rate of change. So really, I'm going to find my a prime of 36 is going to be best approximated by finding the average rate of change of the velocity from 32 to 40. So I'm going to do v of 40 minus v of 32 all over 7 minus negative 4. Nope. All over 40 minus 32. There we go. Remember, we're just doing slope for the average, right? y2 minus y1 over x2 minus x1. And so this is going to be the best approximation for the instantaneous rate of change at 36 seconds. It's not going to be perfect, but it's as close. And that's why they say estimate, okay? Please make sure we indicate units as well at the end. So if I have my velocity, so velocity at 40 is 7. Velocity at 32 seconds is negative 4 all over 40 minus 32, 8. So I end up with, it looks like 7 minus, so 11 eighths. And then we have to do meters per second squared because it's my velocity over second. So meters per second or meters per second squared. All right. In this problem, they have a graph, and they say there are 700 people in line for a popular amusement park ride when the ride begins operation in the morning. Once it begins operation, the ride accepts passengers until the park closes 8 hours later. While there is a line, people move onto the ride at a rate of 800 people per hour. And so the graph above shows the rate at which people arrive at the ride throughout the day. So people are getting here's your line to get onto the roller coaster. So boop, boop, boop. Okay. People are getting onto the roller coaster at a rate of 800 people per hour. And then people are arriving in line at the R of t. That's this graph shown over here. Okay. Time t is measured in hours from the time the ride begins operation. Okay, so they want to know, is the number of people waiting to get in line on the ride increasing or decreasing between t equals 2 and t equals 3? So basically they're asking from this section to this section, is this line getting longer? Like, are more people arriving or are more people getting on the ride? And so you just have to look and compare the rate at which people are getting in line to the rate at which people are getting on the roller coaster. So 800 seems to be the cutoff point. So if people are arriving at 800, 800 people per hour or lower, then that means that they're going to be getting on the roller coaster faster, right? So more people will get on the roller coaster than people will be arriving. Like, it could be that it looks like it's going to rain, so more people are quick getting through the roller coaster and more people are hiding out eating lunch for the day. And so between 2 and 3, it looks like the rate at which people are arriving in line though is much higher. It goes from 800 up to 1200. So that means that the range that this rate takes on is 800 to 1200 people per hour. So that means more people are getting in line than are actually getting on the roller coaster. And what will that end up doing with that line? Well, it'll end up making that line longer and longer and longer. If more people are super excited to ride the ride and are getting in line for it, then that means that the line would be increasing. And so to justify our answer, we could say the number of people waiting in line to get on the ride is increasing because R of t is greater than or equal to 800 for time t equals 2. We'll do this. And so that means that your rate at which people are getting off onto the roller coaster is only 800, but people are getting in line at a much faster or higher rate. And so then that line is going to be increasing. That's a tricky one. At what time is the line for the ride the longest? So basically they're trying to figure out at what time is your ride, or is the line going to be the longest? Now it's going to be the longest when more people have been getting in line, right? Than have been getting onto the roller coaster. So that starts off right away at 0. So there are 800 people per hour getting on the ride, but there are more and more people getting in line, more and more people getting in line, more and more people getting in line. And then be careful, because even though this looks like the maximum number of people that are getting in line, remember this is a rate. So that means that your rate is still just 1200, and our rate is still 1100, and our rate is still 1900. So it looks like right here, that would be when your ride is the longest, because for those first 3 hours of the day, more people were getting in line at this rate than were actually getting onto the roller coaster. So at time t equals 3 hours, that would be when you have the most people in line, because after that the number of people getting in line is increasing still, but it's increasing at a rate less than the number of people that are getting on the roller coaster. And so, excuse me, so the line's growing, 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 and then now the line starts decreasing because more people are getting on the roller coaster, or people are getting on the roller coaster faster than people are getting in line. So we would say that t equals 3 hours. And then let's provide a little bit of justification as well, because R of t was greater than or equal to 600 or 800, excuse me, for 0 to 3 hours, but your rate was less than 800 for t is less than 3. So that means, or excuse me, greater than 3. So that means that your line was increasing up until this point, and then your line started decreasing. So there you go, linear motion. This roller coaster one, is definitely the trickiest one out of all these. You more often see these kind of table problems or graph problems more recently, but I just wanted to throw that roller coaster one on there because I think it's really cool. Awesome. Thanks, guys.